Hello everyone. I hope you're all doing well today. I see some of you are still joining, so let's give it just a moment before we get started. Welcome to Frontline Systems webinar on Analytic Solver optimization. I'm Dr. Sima Maliki and I'm excited to be your host for today's session. Thank you so much for taking the time to be here. We have a lot of great content to cover, so we'll jump right in soon. But just a quick note, since our time is limited, if you have any questions, feel free to send them to consulting@solver.com. That way, we can make sure to address them properly. All right, let's get started. Organizations around the world have been using Frontline Systems products for decades to drive better decisions through optimization. From manufacturing to healthcare, energy to finance, here are just a few ways our tools are used every day, making the most of limited resources like time, money, or equipment, reducing costs, increasing efficiency, and managing risk, scheduling production, deliveries, or staff to improve outcomes and reduce waste. It all comes down to smarter decisions. If you'd like a copy of these slides, just email me at consulting@solver.com and I'll be happy to send them your way. If you'd like a copy of these slides, just email me. In today's session, we'll take a closer look at how mathematical optimization using Analytic Solver can help address complex real-world challenges and how the tools available can support more structured, data-driven decision-making. At its core, this is about approaching problems differently by clearly defining objectives, identifying decision points, and incorporating real-world limitations to arrive at the best possible solution. We'll begin with a healthcare-focused example where we'll assign nurses to hospital wards based on patient demand, nurse specialization, and workload. You'll see how this challenge can be translated into an optimization model and how Solver efficiently finds the optimal assignment. Then we'll explore how Analytic Solver's capabilities extend beyond Excel, enabling you to share, deploy, and scale your models. We'll also briefly highlight the latest AI-assisted features, which provide intelligent, context-aware guidance based on your model structure. Lastly, we'll examine a financial planning scenario involving a pension fund. Using stochastic optimization, we'll address future uncertainty and develop an investment strategy that balances return and risk over time. Before we jump into our first example, let's take a moment to talk a bit about our product line and the tools available to you. Analytic Solver is an all-in-one solution built right into Excel. It equips you with everything you need for optimization, simulation, and data science, all in a single integrated platform. Excel itself is a fantastic starting point. It's flexible, familiar, and widely used. An Analytic Solver works seamlessly across Excel for Windows, Excel for the web, and Excel for Mac, so you can work where you're most comfortable. But to make faster, more accurate, and more scalable decisions, you need more than spreadsheets. You need decision intelligence. Analytic Solver helps you build it with tools that turn your models into actionable insights. And when you're ready to take the next step, you can share and deploy your models with just a few clicks. No coding required. Whether you're creating a web app or scaling for your team, deployment is really simple. Now, for those who do want to work in a programming environment, Frontline offers Solver SDK, which supports a wide range of programming languages, including Python, C, and many others. There's also Raison Decision Services, a platform for building and running models in the cloud using a REST API. And the best part? All of these tools are fully compatible with the models you build in Excel, so your work is both flexible and future-ready. Now that you have a sense of what is possible, let's open up Analytic Solver and start with our first example. Imagine this. A hospital needs to assign 40 nurses to 10 different wards. 4 wards require 2 nurses each due to high patient demand. Each nurse has different expertise. Some specialize in ICU care, others in pediatrics, cardiology, or general care. Staffing must be balanced to ensure optimal patient care while considering nurse preferences and availability. Here's the big question. How should the hospital assign nurses to wards to ensure the best coverage, optimize patient care, and balance workload? This is a typical optimization problem many healthcare administrators face daily, even if they don't realize it. Before we move on, let's take a quick tour of the Analytic Solver ribbon and highlight some of the features we use today. The Model tab opens the task pane, which allows viewing and editing model components and much more. Multidimensional modeling is super helpful when you're working with larger models. Think multiple products, time periods, sources, or destinations. It takes what would normally be a complex and hard to maintain spreadsheet and turns it into a structured, easy to update model. Next is the AI Assist button. When you have a model open, clicking this launches the AI assistant, which reads your model and lets you ask questions about it. For example, you might ask, is my model missing something important? Or how do I add another part to this product assembly? It's a really smart way to get guidance as you build your model. Next is the Simulation tab. On the Simulation tab, you'll find everything related to Monte Carlo simulation and risk analysis. The Distribution button lets you easily define sources of uncertainty using a wide range of predefined probability distributions. The Optimization tab is where we'll spend a lot of time. This is where you define your optimization models, whether you're working with certainty or uncertainty. Analytic Solver also fully supports decision trees, both single and multi-stage, and DMN business rules and decision tables. I'll show you where to find example models for these a bit later. The Parameters tab lets you run multiple parameterized optimizations, handy for scenario testing. The Solve Action tab is where you go to actually solve your models, whether they're optimization or simulation based. On the Analysis tab, you'll be able to review results, generate reports, and create charts to better understand your outcomes. Deploy Model is another great feature. With just a few clicks, you can share your results through Microsoft Teams, create custom visuals, or even connect to Power BI for more advanced dashboards and insights. These deployment tools mean no more emailing workbooks back and forth. You can go beyond static PowerPoints and share live interactive models that update in real time. You can also connect to Tableau or deploy your models as cloud services for web and mobile apps. This is done through Raison Decision Services, a platform provided by Frontline Systems. I'll show you one example of this today, but feel free to email me if you want more details afterward. There's also a built-in AI-powered support assistant based on the same tech as ChatGPT. It's trained on all of Frontline's help content. So whether you're working on optimization, simulation, or data science, it can help you find answers and guide you step by step. And under the Help menu, you'll find a library of ready-to-use examples, everything from basic optimization to stochastic models, decision trees, and more. You can also access user guides and Solver Academy, which offers self-paced courses on all of these topics. Let's also take a quick look at the task pane. This shows your model in outline form where you can review and modify components. Next to that, you'll find the Engines tab, These are the engines that actually solve your models. There are standard built-in engines like LPQP and GRG for nonlinear problems, and also commercial add-on engines like Gurobi and Nitro. You can choose the engine yourself or let Analytic Solver automatically select the best one based on your model structure. Analytic Solver also supports you with tools like Guided Mode, which walks you through the modeling process and helps avoid common errors. Finally, you'll see a log of solution messages in the output pane, and there are a few more helpful options tucked away in the Tools tab as well. Now we are ready to set up our healthcare optimization model. Let's take a quick look at this slide, then we'll jump back into Excel. Solver is powerful, but it needs clear instructions. To get an optimal solution, you must define what success looks like, also known as our goal or objective. Specify what Solver can change, also known as decision variables. Set real-world limitations, or also known as constraints. Once that's in place, Solver analyzes thousands of possible assignments and delivers the best one based on the criteria we set. To set your goal, ask yourself, what is my goal? In this case, our goal is to optimize nurse assignments to balance workload while ensuring each ward is adequately staffed. We need to define the objective clearly. We want to maximize overall efficiency by ensuring each nurse is placed in a ward where their expertise is most valuable. We need to set an objective to maximize nurse satisfaction by incorporating their preferred departments. This is what we call the objective function. Solver will find the best way to allocate nurses based on this goal. In this business situation, we can control which ward each nurse is assigned to and how many nurses each ward receives. In this case, our decision variables are all possible assignments of nurses to wards. Then Solver's job is to figure out the best possible assignment for all to optimize efficiency and workload distribution. Constraints ensure real-world feasibility. They prevent Solver from coming up with solutions that don't make sense. Without these constraints, Solver might suggest something unrealistic, like assigning the same nurse to multiple wards or leaving a critical ward understaffed. Therefore, here are some important constraints for this problem. Every nurse must be assigned to exactly one ward. Each ward must receive the required number of nurses. In some other applications, you can add some nurses may not be qualified for certain wards. For example, a pediatric nurse can't be assigned to ICU. Now let's define the modeled components in Excel using Analytic Solver ribbon. Now let's start with the decision variables for this model. What we're trying to figure out is which nurse gets assigned to which ward. So we need a way to represent that clearly. The best approach here is to create a matrix where each row represents a nurse and each column represents a ward. For example, if nurse 1 is assigned to ward 1, we'll put a 1 in that cell and then zeros in all the other columns for that nurse. This setup makes the assignments easy to see and work with. To keep things clear, I've filled in zeros across the whole matrix to start. Now go ahead and select the full block, then click on Decisions, and now let's select Normal. And as you can see on the task pane, we now have our block of decision variables defined. Now that we've defined our decision variables, let's talk about the restrictions we have. Well, in this model, we're making yes or no decisions. We're asking whether a nurse is assigned to a particular ward or not. This is what we call a binary decision. In optimization and specifically in Analytic Solver, we can tell the software, hey, each of these cells should be either a 0 or a 1, nothing in between. And setting this up is easy. Let's select the block of decision variables we created earlier, then click on Constraints, choose Variables, and you'll see several options like integer, binary, and more. In this case, we'll choose binary. Now let's take a quick look at the task pane under the Model tab, and there it is. Our binary constraint has been added to the model. Next, we need to make sure that each nurse is assigned to exactly one word. To do that, we'll add a sum function for each nurse. I've created a column labeled totals for this. In cell Y13, let's sum all the assignment values across the row for nurse 1, then copy that formula down for all the nurses. Once that's in place, we'll go to the Constraints tab, click Normal Constraints, and set up the rule. The sum of assignments for each nurse must equal 1. In the dialog box, the left-hand side is the total assignments. We choose equals for the sign, and then enter 1 as the right-hand side. Click OK, and we're done. You can verify that this constraint has been added by checking the task pane. Now let's move to the ward requirements. Each ward has a specific number of nurses it needs, so we'll sum the assignments down each column to see how many nurses are assigned to each ward. Again, because we're using binary decision variables, this is very straightforward. 1 means assigned, 0 means not. Once we've dragged the sum formulas for all wards, we'll select that block, go to Constraints, choose Normal, and then set the condition. The total assignments to each ward must be greater than or equal to the requirement listed in row 28. Click OK, and now we've added all the key constraints to the model. Let's move on to the objective function. What we're trying to optimize. We have a matrix of nurse preferences. A score of 1 means a nurse really wants to be in that ward. Higher numbers mean less preferred. Our goal is to assign nurses in a way that minimizes the total preference score, so we're giving nurses as many of their top choices as possible. To do this, we'll use a function called SumProduct in Excel. In cell Z13, we'll calculate the sum product of the preference scores and the assignment values for nurse 1. Then copy that formula down for the rest of the nurses. Now let's add up those values to get the total preference score. This is our objective. We'll select that cell, click on Objective, choose Minimize, and select Normal. And that's it. We've defined our full optimization model because we're using binary decision variables and linear formulas. This is what's called a linear mixed integer model. That just means we're mixing yes-no decisions, binary, with linear relationships in the objective and constraints. Why is this important? Because it helps us and Solver pick the right solving engine, and here's where Analytic Solver makes life easier. It supports you step by step. Let's click Optimize and use Guided Mode. Solver will now analyze your model and diagnose its structure. It'll even recommend the best solving engine based on your model setup. You can also check the box for automatically select engine if you'd rather let Analytic Solver choose the best option for you. Click Next, and here we go. We have the optimal solution. You'll see that each nurse is assigned to exactly one ward and all ward requirements are met. There are also plenty of reports and charts available for you to explore at your own pace. Any questions so far? Looks like we're good for now. But if anything comes up later, whether it's a question, a roadblock, or just something you're curious about, please feel free to reach out to me or contact our support team. We're always here to help. We've just defined our first optimization model. I hope setting it up felt straightforward, especially for those of you who are new to our software and maybe even to optimization in general. Now, before we go further, I want to share something important that will make a real difference in your success with building and solving optimization models. How you define your objective and constraints can directly affect the quality of your solution, the performance and speed of solver in finding that solution. This is where the art of modeling comes in. I'll walk you through a few key insights now, but if you're eager for a deeper dive, check out the user guide, Mastering Optimization Techniques. You can find it by clicking Help, User Guides, Analytic Solver User Guide. Scroll down to Mastering Optimization Techniques chapter or Best Practices for Building Large-Scale Models. You are also welcome to watch one of our detailed webinar recordings on the Frontline Solvers YouTube channel. Let's find out why model structure matters. The structure of your model plays a critical role in determining which solution method solver uses and how efficiently solver can find the best solution. To explain this better, let's look at the three main solving methods in Analytic Solver. Let's start with simplex LP, linear programming method. This method assumes that the formulas calculating your objective and constraints are linear functions of the decision variables. When your model is truly linear, solver can quickly find the globally optimal solution. Starting values of decision variables don't matter. This method will always find the best solution. Linear models are fast and reliable. When possible, reformulate complex models to maintain a linearity. For example, avoid if functions if the logical part depends on decision variables. GRG, nonlinear or generalized reduced gradient method assumes that the formulas for the objective and constraints are smooth, linear or nonlinear functions. An evolutionary or genetic algorithm method makes no assumptions about how the formulas behave. Solver explores many possible solutions, but it can only find a good solution, not necessarily the globally optimal one. If you use the simplex LP method on a truly linear model, you'll always get the optimal solution. But with the GRG nonlinear or evolutionary methods, starting values and model structure can impact the outcome. Let's explore this in action. I'll go ahead and manually select the GRG engine and uncheck the automatically select engine option. Now let's click on solve and see what happens. Here's what we get. Analytic Solver immediately analyzes the model and detects that this is a MIP mixed integer programming problem. Since GRG isn't the right engine for this type of model, Solver alerts us and suggests better alternative engines to use. This is great. Analytic Solver not only noticed the engine issue, but is also recommending the best alternative engines that are better suited for this model. Now let's choose LP quadratic engine, and here are the results. This is a perfect example of how Analytic Solver doesn't just solve your model, it also helps guide you toward the best solving method, ensuring optimal results every time. Now that we've used Analytic Solver to build and solve an optimization model and seen the results, let's take the next step. How do we share these results with others in a way that's repeatable, manageable, and easy to access? Of course, you can always share the spreadsheet itself, but Analytic Solver offers something much more powerful, something that lets you take your Excel model to the next level and make it available wherever and whenever it's needed. This is possible using a cloud platform from Frontline Systems called Raison Decision Services. With just a few clicks, right from Excel, you can deploy your model to the Raison server, a cloud-based service that exposes your model through a REST API. You don't need to write any code. You can even test the model right there in Excel. With the deploy model options, you can turn your spreadsheet into a cloud service in seconds. This is just one option. We've built multiple examples to show how flexible deployment can be. You can host your results in Microsoft Teams, embed your model into a custom web app, or call the Raison service from Power BI, Tableau, or your own applications. Let's walk through a few of these options. Let's try Teams first. If you want to share interactive model results without sending the full workbook, you can send a Teams report that includes only the key results and links back to your original model. To do this, first make sure your workbook is saved to a shared location, like OneDrive or SharePoint. Solve the model and save it. Teams won't be available until results exist. Click Deploy Teams report to choose which model components to include. Use the arrows to select exactly what you want to share. Click OK and choose your team and channel. Type a custom workbook name and message and hit Send. Analytic Solver will automatically generate a new workbook with just the selected results, link back to your model, and post it directly to your chosen Teams channel. Your colleagues can then open the report inside Teams, in Excel desktop, or in Excel for the web. If anything changes, you simply resolve your model and click refresh. No need to create a new report each time. This is just one way to collaborate more efficiently, and you can even customize the report's design if you'd like. We also support Power BI and Tableau integrations, but for time's sake, I'll skip those demos here. You can find a detailed walkthrough of those on our YouTube channel. Feel free to check it out anytime. If you're not sure which deployment path to take, the deployment wizard can guide you step by step through the available options and help you choose what works best for your needs. Now let's try publishing our Excel model to the cloud as a service. We'll select Deploy, Cloud Service, Excel Model, give our model a name and save it. This uploads the workbook to the Raison Cloud, saving it in your account. Once it's uploaded, Raison.com automatically opens and displays the model. Without translating anything, it's still your Excel file. What's happening here is powerful. Your spreadsheet model has just been promoted to a cloud service. Raison is a web-based platform that runs behind the scenes as a REST API. It can be called from any application to run optimization, simulation, forecasting, or scoring. Raison.com, the front-end interface. Raison.net is the engine behind it, allowing models to be solved from a browser, an app, or another platform. You can even submit models to a queue and retrieve results in JSON or OData format. Now let's turn our model into a working web page. From the ribbon, click Deploy, Quick Test, Web Page. Analytic Solver translates your Excel model into Raison language and instantly opens a browser-based web application, complete with input fields, solve buttons, and live results. This is a standalone HTML file using simple JavaScript with the logic of your model embedded inside. You can right-click and view the page source to see exactly how it works. Clicking Solve sends your model to the Raison server via a REST API call. The results come back live in the same way they would inside Excel, and just like that, you've built a functioning web app from an Excel file in just a few clicks. No developers, no back and forth, no rebuild. All of this, Teams reports, cloud deployment, custom apps, web pages, is what we call model deployment. And it's one of the most powerful ways to extend the value of your work and make it easily accessible to others. If you'd like more info, just let me know. I'm happy to walk through specific examples with you or send more resources. Now let's pause on deployment for a moment and shift gears. Let's now turn our attention to a powerful concept in advanced optimization: stochastic optimization. Before we jump into the example, let's take a few minutes to understand what stochastic optimization is all about in a very practical sense. In traditional models, we assume that every number we plug into our model, every demand, cost, or return is known and fixed. But as we know, real life doesn't work that way. Especially in finance, uncertainty is the norm. That's where stochastic optimization comes in. It helps us build models that account for uncertainty and still deliver smart decisions. The good news is that Analytic Solver has the full spectrum of capabilities for analyzing and solving decision models that must allocate scarce resources in the presence of risk and uncertainty. Uncertain parameters might be computed from a primitive uncertainty such as a future interest rate or rainfall amount. We will call this an uncertain variable, and in Analytic Solver, we'll use the uncertain variable dialog to define and quantify this primitive uncertainty. Let's discuss this little further. A certain parameter has a single known value. You can think of an uncertain parameter as having many possible values. We call each such value a realization of the uncertainty. In this slide, I have pictured one certain and three uncertain parameters. Let's look at a real-world financial example. Click on Help, Examples, Stochastic Optimization Example. Let's scroll down and open this ready-to-solve model. Pension Fund Asset Liability Management. You're managing a pension fund with $250,000 in capital. Your goal is to invest this amount in 3 bonds, each with fixed purchase prices and known coupon payments in order to fund future liabilities. Retirement payments due each year for the next 8 years. The tricky part? Those yearly liabilities are uncertain. They're modeled as normally distributed random variables, each with a known mean and standard deviation. So here's the question. How should we allocate our capital across these bonds today to maximize leftover cash at the end of 8 years while meeting liabilities with at least 85% probability? That's where stochastic optimization comes in. Let's walk through each component of this stochastic model, beginning with a brief discussion on constraints. When uncertainty is involved, constraints can get more interesting. We essentially have 3 categories to think about: normal constraints, chance constraints, and recourse constraints. Normal or deterministic constraints are constraints that don't involve uncertain variables. They're just the usual formulas saying x plus y must be less than z, and so on. If all variables are known and fixed, you simply ensure the constraints hold under those conditions. If a constraint depends on uncertain variables, like our annual liabilities, and normal decision variables, like how much we invest in each bond, we have to decide what it means for the constraint to be satisfied. Here, we are using a value at risk chance constraint, which dictates that each year's available cash must meet that year's liability 85% of the time. Of course, in the remaining 15% of scenarios, there's no explicit limit on how far below the liability we could be. If we want to also manage the severity of losses in that tail, we could switch to a conditional value at risk approach. What's really exciting is that Analytic Solver is uniquely powerful for both deterministic and stochastic optimization. This demo is just the tip of the iceberg. Once you master these capabilities, you'll see why Analytic Solver stands out as the best tool for building robust, risk-aware optimization models. To set up chance constraints, you'll just go to Constraints in Analytic Solver and choose the chance option. Next, we have our decision variables, which in this case represent how much to invest in each bond today. These are standard or normal decision variables. For our uncertain parameters, we have annual liabilities modeled using a normal distribution. These are the amounts the pension fund must pay out each year, fluctuating around some average. To enter a normal distribution, simply click Distributions and then Common. You'll notice we support over 50 different distributions. If you're unsure which one to choose, click on the Distribution Wizard for guidance. Now let's talk about our objective function. Starting in year 1, if you look at cell D31, you'll see the coupon payment for bond 1 plus the price we pay for that bond. We apply the same logic for bonds 2 and 3. In cell G31, we use a sum product function to combine those amounts based on our decision variables, i.e. how many of each bond we decide to buy. Next, we calculate remaining capital by taking our initial capital and subtracting the predicted liability for year 1. Then total cash flow is simply the sum of our total bond yields plus that remaining capital. Moving into year 2, we do something similar, but now we factor in both year 1 and year 2 liabilities. You'll notice psi output in these cells. Double-clicking on any of them runs a simulation with 1,000 trial values, giving us a histogram of possible outcomes for remaining capital. It also offers detailed statistics, mean, standard deviation, percentiles, you name it. Over on the sensitivity tab, we have a tornado chart showing which inputs most strongly affect cell H31. Unsurprisingly, the liability in cell H16 has the biggest impact. Higher liability means lower remaining capital, which makes intuitive sense. Finally, our total cash flow at the end of year 8 appears in cell I38, and we want to maximize that amount across all scenarios. So in cell I39, we calculate the expected cash flow and tell Analytic Solver to optimize it for us. And in column K, you'll see how we use the SciTarget function to calculate probabilities, like the chance that we'll meet certain liabilities. Now let's click on Optimize using guided mode. You'll see Analytic Solver analyzes our formulas and detects that we're dealing with a stochastic optimization problem. Moving on by clicking Next, you'll notice it provides a wealth of information. Our original model is identified as a stochastic linear programming model with chance constraints, and Analytic Solver automatically transforms it into a larger, robust counterpart, creating a deterministic equivalent that captures all our uncertainty considerations. The LPQP engine then finds an optimal solution to this robust version of the model. The solution is then tested against the original stochastic model via Monte Carlo simulation, revealing that it oversatisfies our chance constraints. We aimed for 85% reliability, but we're actually seeing satisfaction levels as high as 99% or 100%. That's quite conservative. If we want to see whether relaxing these constraints can boost our objective, we can use the Auto Adjust Chance Constraints feature. It is a green play button in the Task Pane Output tab. Activating this tells Analytic Solver to resolve multiple times, adjusting the size of the uncertainty set in search of a better solution with higher expected cash flow. Before doing that, let's check out the answer report. Click on Reports, select Answer Report. You'll notice that most constraints are satisfied 100% of the time, and one constraint is satisfied at 99.8%, both of which are actually more restrictive than our original 85% target. Here's the expected cash flow. Next, we'll return to the model and click Auto Adjust Chance Constraints. You'll see Solver internally tests different satisfaction levels, maybe 85%, then 82%, then 80%, and so on, and compare the outcomes. If it finds that a particular satisfaction level, say 82%, is actually below our required 85%, it will reject that solution. Finally, we generate another answer report. Now you'll see we've landed on around 86% satisfaction for the constraint, still above our 85% requirement, but our objective has improved noticeably. This demonstrates how auto-adjusting chance constraints can lead to better results, balancing risk tolerance with higher returns. Today, we started from scratch and built an optimization model for a scheduling application in healthcare. However, the concepts and techniques we explored can also be applied across various industries such as call centers and staff allocation. We then progressed to a more advanced topic on stochastic optimization, at giving you a spectrum of what can be accomplished from deterministic optimization to stochastic optimization, all within Excel. The process remains simple, straightforward, and requires no programming. Excel makes it easy to begin your analytics journey, build your first models, and demonstrate a proof of concept effectively. Here are a few key takeaways. Analytic Solver runs on Excel for Windows, Excel for Mac, and Excel for the web. Everything is transparent, and it's not a black box solution. Scaling up your models is simple. Analytic Solver offers a full range of capabilities to analyze and solve optimization models that involve allocating scarce resources under risk and uncertainty. Analytic Solver provides cutting-edge technology for stochastic programming and robust optimization methods with performance that's significantly faster than its competitors. It also offers unique capabilities to define and solve problems with wait-and-see or recourse decisions. If this topic interests you, feel free to explore our YouTube channel for previous recordings or contact me at consulting@solver.com for more information. Without the right tools, solving resource allocation problems under risk and uncertainty can be both difficult and expensive. However, now that you've experienced what's possible with Analytic Solver, you know that the power to solve large-scale optimization problems with or without uncertainty is already at your fingertips in Excel and beyond. We also demonstrated that you can effortlessly deploy your models to the cloud and build custom applications. Explore new possibilities using Raisin Decision Services, another cutting-edge solution from Frontline Systems. With Analytic Solver and the power of Raisin, you can promote your models to run on the Raisin Cloud service, making results easily accessible to others. What's next for you? Start a free trial, get hands-on experience with ready-to-solve examples even during the trial period. Explore user guides. Analytic Solver's user guides are well-written, concise, and packed with helpful insights. If you're interested in more in-depth learning, we offer optimization courses at Solver Academy. We invite you to take the opportunity to explore our other free webinars on simulation and data science, where you can further enhance your ability to make data-driven decisions. These webinars are designed to help you deepen your understanding and apply advanced techniques with ease. As we wrap up today's webinar, I encourage you to reach out with any questions. If you prefer to ask questions offline, feel free to send them, and I will follow up with responses after the session. Below is the contact information for myself and key team members. We look forward to helping you achieve your goals. Thank you for your time and participation. Are there any final questions before I conclude the webinar? I will now end the session and will respond to any questions posted later or emailed directly to me. Looking forward to connecting with you. Have a wonderful rest of the day and goodbye for now.